so much, and thank you very much for the invitation. I've been enjoying my time in Taiwan a lot. So today I will talk about the scattering waveform at order t to the 3, including spin corrections up to spin squared. This talk is based on a paper from Christmas Day from last year, plus some ongoing work that hopefully will be out on the archive by January. Right, so here on the left, we see a system of a binary black hole that we learned a lot about this morning. So this is a bound system, two black holes gravitationally bound in spiral and merge. And in the process of doing that, they emit this sinusoidal gravitational wave. It can be picked up by gravitational wave detectors. Now on the right is a somewhat similar system, except that these two black holes, they are unbound. So that means they start from being infinitely apart with some impact parameter. They get closer. Once they get close enough, they influence each other's trajectory. They deflect this trajectory, and this burst of gravitational radiation is emitted. That is obviously not sinusoidal. Now, in both of these systems, these guys, they are called the waveform. It's very crucial that we know what these look like for measurements in LIGO, Virgo, Cagra, because there is so much noise. So we actually have to know what we're looking for to observe it. Thus, modeling this waveform is extremely important. Today, I want to focus on the in-spiral part, or the part where these two black holes are far apart. For the bound system, the best method to use there is the so-called post-Newtonian expansion. What's special about the bound system is that here the virial theorem holds, and this tells us that when fields are weak, velocities are also small. So the post-Newtonian expansion is an expansion in these two parameters, small velocities and small gm over r. In the unbound system, we do not have this virial theorem holding anymore, so we can get scatterings at very high velocities. Thus, we must generalize this post-Newtonian expansion. And what works best at large separation is this post-Minkowskian expansion. That is, once again, an expansion in the weak field, but we do not assume small velocities anymore. Well, the first kind of source has been observed. The second one has not. But I want to explain why we should still care about this scattering of black holes. First of all, we can just hope that in the future, where we will have new detectors that work on higher precision and different frequency ranges, we can directly observe scatterings like that. Furthermore, in simulations like this one up here, has been found that some black holes get captured, so the initial part is actually a scattering, where the post-Minkowskian expansion is useful. Also, orbits with high eccentricities have been seen, and as shown on this plot, eccentricities close to 1, post-Minkowskian expansion is actually superior to the post-Newtonian one. Furthermore, we can hope to learn about the bound system by using information from the unbound one, by either mapping observables directly or mapping Hamiltonians. It can be used as input into the effective one-body formalism. And finally, post-Newtonian waveforms tend to be slowish to evaluate. The hope is that with the post-Minkowskian expansion, resumming velocity contributions, we can find analytic waveform templates that are fast to evaluate. So the goal of my talk is to explain how we can get a time-dependent waveform as an expansion in this parameter gm over b. And the very broad idea is we want to solve this classical scattering system order by order in G. And the method to do that is to use the QFT as a quantized system, use a Feynman diagram approach to solve this iteratively, and then take a classical limit, map this back to the classical problem, and get this classical waveform observable. As it says in the title, I also consider spin corrections. And that's also very easy to incorporate in this QFT approach. Instead of using massive scalar fields for black holes, we use massive tensor fields. By using a tensor field of spin s, we can actually get spin corrections up to 2s. Furthermore, these spin corrections show up in the specific form where they are also suppressed by impact parameter b. So they are equally suppressed as the corrections in G, and hence are equally important if we want to consider the counting in suppression by impact parameter. As a summary, which is the end of this introduction, this is what we know so far about Post-Minkowskian waveforms. And it's nice to see, so in the 80s, there was the first leading order spin of scalar waveform known that was derived classically. And then these waveforms really exploded once the scattering amplitude approaches were introduced to the problem. First, the leading order piece was recomputed in 2021, and spin corrections were added. And then last year, also the next leading order was computed. We added the first spin correction, and this talk will actually be largely about how to add the spin squared correction to this next leading order piece. Having finished the broad overview, I will now go to explaining how we can extract waveforms from scattering amplitudes, and I will explain two ways. First, using K-mod, and the second one that actually Benjamin already introduced using word-line formalisms. So K-mod, named after Kosover maybe, and O'Connell, is the approach where we can directly extract observables from scattering amplitudes. And it relates the waveform directly to the Fourier transformation of these two pieces that look like amplitudes or similar to amplitudes. Now, the first one that is linear in the transition matrix T is actually just a 5-point amplitude. And if we want to get up to 3 p.m., which is what this talk is about, we need up to 1 loop diagrams. This is what I call the amplitude contribution. Now, the second part, the blue part, looks a bit more complicated. It's quadratic in T. The trick is, we want to evaluate this, we insert a complete set of states in here. And then this starts to look like the cut of this 1 loop amplitude up there. These two have to be added. And now if we want a time domain waveform, there are still plenty of Fourier transformations to be done. One from momentum space to impact parameter space, and the last one from frequency domain to time domain. Now, adding this cut turns out to be somewhat easy to do if we do it on the integral level. So the 5-point amplitude that I showed only has integrals coming from these 4 parent topologies, A, B, C, and D. And these 4 topologies, if you look at them, are related by exchanging the external particles. In the classical limit, this amounts to some sign changes of the integrals. Furthermore, in the classical limit, or here the iconal limit, these integrals are all equivalent up to the prescription of the I epsilon. Then we need to add this cut that adds, instead of 2 massive propagators, adds delta functions. By doing this weighted sum that is determined by the signs of the coefficients of these integrals, we find that we always end up with one of the massive propagators turning into a retarded propagators and the other one turning into a delta function. The gravitons, on the other hand, remain Feynman propagators. What is important in this approach? The only amplitude contribution has so-called hyperclassical terms. It means if we take a classical limit, so we send masses and charges to infinity, this actually diverges. This pieces only get subtracted once we add the cut contribution, and we do this weighted sum and add these integrals together in this specific way. Right, now the second approach to extract observables, Benjamin introduced nicely just before the break, is from word-line theories, and it's this 1-point function of this graviton being emitted. So what is different in word-line theories is we have now gravitons coupled to world line trajectories. And if we want to measure the waveform, we just look at diagrams where one of these gravitons is emitted at the end and is on shell. And to get observables, we use the informalism, and that turns all these diagrams causal. So there is a causality flow towards the outgoing graviton. That means these are retarded propagators. So what I'm showing here, this is actually a three-body waveform. So why? We also already heard, to do the classical limit in this word line formalism, we need only to consider trees and not loops. Loops give quantum corrections. G to the 3 contribution now comes from coupling this to 3 background trajectories. In fact, the whole three-body waveform given by these 15 diagrams and some perturbation. Okay, if we actually want the next to leading order correction to a two-body waveform, we only need to identify some of the background fields with each other. So we say now, okay, background field 3 has the same initial conditions as number 2. What this does is it actually turns this into something that looks like a Feynman integral. So this is my favorite diagram. It fulfills these 3 energy conservation constraints that I show as delta functions by now identifying initial velocity 2 with initial velocity 3 and doing this suspicious relabeling of Q2 as L and Q3 as Q2 minus L. One of these delta functions turns into this here, V2.L. So by reverse unitarity, we would see this is a Feynman-like diagrams, and it's very similar to what we got earlier doing K-Mach QFTs. This is the prior topology that comes out if we want to compute this waveform from the world line theories. We have this delta function, like before, for one of the massive propagators. We have a retarded massive propagators. Now, as compared to before, we have actually retarded graviton propagators instead of Feynman propagators. And that could be a problem, since that could mean we have some zero graviton modes that contribute and that give us a different result. Now, it turns out it's not a problem. So to remind everybody, what is the difference between Feynman propagators and retarded propagators? Feynman propagators come in with a plus I epsilon prescription, while for retarded propagators, it depends on the sign of the energy flowing through the graviton. Okay, now this whole diagram, it comes with momentum and energy conservation constraints. By going, so these here, we go here. By going into the rest frame of black hole 2, we can see that that means energy components of this line is 0, and if this line is 0, it doesn't matter which of these propagators we choose. Furthermore, the energy component of this line is equal to that of the outgoing graviton, so it's positive, and the I epsilon line is that of a Feynman propagator. Thus, we can just replace all these retarded propagators by Feynman propagators and recycle the integrals that are, by the way, already known, that have been used for extracting this waveform in the field theory. Okay, so having established these 2 ways of getting waveforms, and we know how we compute the integrals, now we need to worry about how we get the amplitude. I will also show again 2 approaches. First, we can either get this from doing 5.1 loop amplitudes or doing trees. I will start with what we did in our first paper last year. We used quantum field theory to get up to spin squared corrections when it's a minimally coupled Proctor field and couple that to Einstein-Hilbert, to the Einstein-Hilbert action. Kinematics for this 5-point we chose in such a way that we use these barred momentas or averaged momentas. These make it very easy to take the classical limit of the amplitude, but we only have to send their masses to infinity and pick out the classical term. What makes this problem hard is that it's a very multi-scale problem. In fact, we have 7 irreducible scalar products that we need to worry about. What makes it also a bit hard is that by using this Proca theory, the amplitude is expressed in terms of polarization vectors instead of classical spin. But we want a result that, well, we have some correspondence to the spin of a black hole. So the trick here is to first write all polarization vectors in the same frame. So we take the ingoing as the polarization vector that's in the frame of the ingoing one and that of the outgoing one, and boost it to that of the averaged momentum. Once they are in the same frame, we can do a Glebsch-Gordon decomposition into a scalar representation, an antisymmetric representation, and symmetric traceless representation, where we write it in terms of this Pauli-Lubanski operator. The classical spin we then find as the expectation value of this Pauli-Lubanski operator, so we can get up to here in squared corrections. Now, computing the amplitude, we use this approach of numerical unitarity. At the heart of numerical unitarity lies this integrand equation here, where the right side is a decomposition into master integrals and surface integrals. The master integrands in our case are scalar integrands, so it's the box, it's the pentagons, triangles, and so on. Surface integrands we call terms that integrate to 0 because of IBP relations. Again, this equation tells us that we can find the coefficients of these master integrands by evaluating only trees. So for example, for this box here, we need to sum over the topology of the box and all topologies above it, which are pentagons. And this is then equal to the product of the trees corresponding to the vertices of this box. Now, this numerical unitarity equation, it is implemented in this called parallel here. And in a finite field, it computes numerical values for these coefficients. To get a fully analytic result, we have to reconstruct these coefficients. We know these coefficients must be rational functions in the seven scalar products that I showed earlier. And we have to reconstruct it. Now, most important is actually the reconstruction in the Barth mass, because this lets us pick out the classical piece, and then we only have to worry about that and reconstruct that. Now, this approach worked nicely, linear in spin. It doesn't scale great computationally once you want to go higher. So at spin squared, it became expensive. And we decided, first of all, we want to validate our results, and also we're just interested in learning something else, to also use the wordline QFT. The wordline QFT was also introduced this morning by Benjamin. The action that captures up to spin squared effects is this one here. The spin is related to this world line. So there is background field psi and a quantized fluctuation on top of it, phi. From this wordline QFT action, we can derive Feynman rules. And from Feynman rules, we can then put together these 3-body trees that are the input into what we need to extract the waveform. So we then identify here, well, first of all, we have to do all permutations of 1, 2, and 3, and then identify always 2 of these background fields with each other. And this gives us directly analytic results for the waveform. Since we are big fans of QFT and validating things, we found, well, we can also do this using Caravelle. So while also computing these trees in wordline QFT, these actually are equivalent to computing these 7-point trees of the 3-body scattering using a minimally coupled Proca theory. Now, what is great about this is we do not have to do all these cuts, we do not have to do all these loops, we do not have to subtract any hyperclassical terms. We directly get this classical tree, and then we can just reconstruct. We have to reconstruct the coefficients of the form factor. So form factors are the combinations of polarization vectors. So we need to construct these coefficients an and only pick out the classical piece. Pick out the classical piece, we must do this reconstruction in Barth mass. But it turns out this computation is scaled way better than to reconstruct the entire amplitude. For example, to get the scalar result, we only needed to go up to like number 24 here and 18 down here. For linear in spin, it was only up to 30, and then at spin squared only 36. This is really easily scalable to higher spin. It's also easily scalable to higher loops. So it's possible to, for example, check a 5 p.m. integrand that is input into that is broadline QFT. We just get a numerical check using Caravelle. Which brings me to our results. Yep. Okay, so our results are in momentum space at the moment. All of them up to spin squared are structured in the following way. We get a tree piece, we get an infrared pole, we get a UV pole, we get a tail, and a finite piece. And the plots here are after Fourier transformation, what the scalar tree and the scalar finite piece look like, so what one could technically observe in the gravitational wave detector. We were very careful validating all these results. So first of all, we checked with other groups that also did the scalar piece and got agreement. 2 papers furthermore checked the scalar piece using more classical approaches, so the MPM formalism, and also found agreement. This has not yet been done for linear in spin and quadratic in spin. We checked gauge invariance of our waveform and found that it works everywhere. We checked the infrared pole, so we expect the infrared pole to scale with the tree and with this Weinberg-Soft vector. Now, this is not standard Weinberg-Soft vector, since the Weinberg-Soft theorem is the theorem for amplitudes. So the normal Weinberg-Soft theorem tells you that this coefficient can be found by summing over contributions from diagrams where 2 of the external legs exchange a soft graviton. If we want to apply this to observables, we have to first subtract the cut that we saw comes out of K-Mach here. So this cut is only the second diagram and adds this vector down here. Sorry. Weinberg-Soft vector. It agrees up to linear in spin. We're currently still working on checking it at spin squared. Furthermore, there is a UV pole. This UV pole we want to be finite, or we want to disappear because we want our observable to be finite. And we find that this integrates to a contact term up to spin squared at spin 1. We're currently still checking it at spin squared. Finally, we validate all these computations we do using the wordline formalism in Caravelle. Once again, done for linear in spin. Spin squared is still work in progress. Okay, now to circle back to the beginning, where I gave some motivations why this problem is interesting despite not being observed yet. I just wanted to make a quick example to show how important this next to leading order effects can be. My example is we take a primary black hole with the mass 5 times 10 to the 4 solar masses, put it somewhere into the center of the Andromeda galaxy, and then let a secondary black hole with 50 solar masses scatter of it with an impact parameter of 1,000 Schwarzschild radii. This has a peak frequency around 10 to the minus 4 hertz, and that perfectly falls into the LISA band. Purple line here shows the sensitivity that LISA will have. And the leading order piece comes in at 10 to the minus 13 in strength. The next to leading order is at 10 to the minus 15. So the next to leading order will be here. And well, this is not a proper data analysis, but just the fact that this is above this noise curve gives us a hint that such a system could technically be observable with LISA. To summarize, in this talk, I described two methods to extract waveforms, either from field theories or from word-line formalisms. I explained why we can recycle the integrals that are known to work for field theories also for word-line quantum field theory. I showed that if we want to avoid hyperclassical terms, we might just use trees to get the integrands for the waveform. And finally, I gave an update on how our validation is going of our results up to space squared. Now, what I'd be very interested in to see in the future is a check of the spin-corrected waveforms also against these classical methods of the NPM formalism. There are a lot of additions that can be done to these waveforms. One can do the Fourier transformation better at higher loop effects, at higher spin effects, at finite size effects, and so on. And whoever is a bit impatient, it would be great to find mapping to the bound system, which I now learned about from the last talk, can also be done for the tail term, and make this directly applicable to the LIGO-Virgo-Caldera research. Thank you very much.
Thanks for a nice talk. Any questions for Lara? Okay, maybe I'll start with one question. So can you comment on the Fourier transform? Because, for example, at tree level, there's this nice paper that would turn the Fourier transform into cuts. Can you do something here at 1D that might help you?
I think so. I mean, there was a paper by Stefano doing this. So I'm sure this can be done for this Fourier transformation. So you can do this differential equation method and solve them analytically. Sure, this can be done in one loop. Not sure done in two loops.
Other questions for Lara?
Have you thought about calculating the waveform for this three-body process?
Or can you repeat?
Have you thought about calculating the waveform for this three-body process?
We have, yes.
Have you calculated?
We haven't started, so feel free to do it. But yes, it's absolutely doable. You just get more Fourier transformations to do there.
Yeah, the Fourier transforms are much harder. But...
Yes, but you don't have to do the loop.
Okay, if not, thanks Lara again.